So we're gonna do let's see. This page of notes 16, it looks like this. So pull that out and I'm gonna show you some YouTube videos. Share screen. Yes, please. This one, share. I don't need the Zoom meeting anymore. This one. No sound. So this is another video that's showing a precipitation reaction. We have, here's what's happening. We have copper sulfate plus sodium hydroxide making copper hydroxide and sodium sulfate. Both of the reactants, the copper sulfate and the sodium hydroxide, let's see if I can fix this. Not really, it still shows that bar in the middle. But anyway, the copper sulfate and the sodium hydroxide, those are aqueous. We know that because they're coming together, they're mixing, they're already in these solutions. Copper hydroxide, sodium sulfate, one of those is not soluble because watch what happens. We're getting a precipitate forming. You see that blue? Ooh, that's pretty. That was cool. Let me go back because I want to see that again. So I'm thinking that the copper hydroxide is what's blue in there. Reason number one is because the other component, this sodium sulfate, sodium is a 1+ ion. So those are going to be soluble. All right, let's see. Okay, back to that video because it was really cool. Here's another one that's happening. We have silver nitrate and potassium chromate. Those two aqueous are mixing together to make potassium nitrate and silver chromate. I'm thinking the silver chromate is that orange because the potassium nitrate, nitrates are always soluble, and potassium is in the +1 column. It should also be soluble. Looks so cool. So he just has the one and he's dripping the other into it to mix them. You could just mix them together, but it would not look as cool aesthetically. It would look like this, which I don't think is as cool. This one, ferric chloride, that means iron, iron chloride and potassium thiocyanate. I don't even really know what those are, but I bet that the potassium chloride is the one that is clear and the iron thiocyanate is that orange color because iron's already kind of orange. So I'm a little bit thinking that that's the orange here, but potassium is a 1+, so it should be soluble. That one looks cool. It looks like blood, which has iron in it. So check that out. That's cool. I love it. Got any more? Wow, he just put it on all at once. Oh, that was too fast of an equation there, buddy. Lead nitrate plus potassium iodide is lead iodide and potassium nitrate. Lead iodide is the yellow. That looks so cool. We should for sure do a lab with this stuff when I get back. We got to do all the fun labs when I get back, so that way you can like look forward to me coming back. Any more? And I think the end of it is just him talking. Okay, So what we're going to work with today on this piece of paper is we've got two beakers. 1, 2. They're going to be aqueous solution, aqueous solution. We're going to mix the contents of each beaker into a bigger beaker and see, would they precipitate like in those videos, or would they not? So here's the paper we're working with. And I'm going to ignore the top for a second. We're just going to start here. Will there be a precipitate if 80 milliliters of 1.0 times 10 to the negative 5 molar barium hydroxide is added to 20 milliliters of 1 times 10 to the negative 5th iron sulfate? All right, so we're going to make the assumption that the barium hydroxide is dissolvable, and it is dissolved because it says AQ right there, but also to have a precipitate reaction, precipitate reactions happen when you have aqueous plus aqueous, two aqueous solutions, they mix together, and then you get a solid. You can still have an aqueous as well, but one of the things needs to be a solid. So here's one of our aqueous solutions. Here's the other. We're going to do some calculations on them separately. So that way, when we mix them together here, we can determine if a solid is formed or not. All right, so let me get my windows all straight here. It's actually kind of hard to do this because I have to have like multiple windows open to record these videos. Will there be a precipitate if 80 milliliters, I'm going to convert that right away. I don't want to deal with milliliters. Just get rid of milliliters, put it in liters, divide it by 1,000. So we've got 0.08 liters. I think, did I get that right? 80 divided by 1,000, 0.08. Yep. So we have this much volume of this concentration of barium hydroxide solution. That's what's going on in this beaker. So I'm going to write that out over here inside of the actual beaker. I have, here's my, like my water line. And in here, I have 80 milliliters, but I already converted that. So 0.08 liters of 1.0 times 10 to the negative 5th molarity of barium hydroxide. When barium hydroxide breaks apart, here it is all together, BaOH2. But down here, I want to show how it separates. I'd have 1 barium and 2 hydroxides, because it's barium hydroxide with the little 2. So here we go, 80 milliliters of that. That's what I have drawn. Your turn, do the exact same thing, but we're going to do it for the iron sulfate. We have 20 milliliters of same concentration iron sulfate. I'll do it with you, but try and not peek too much at my screen here, unless you need a hint. When this breaks apart, I'm going to have 2 irons and 3 sulfates. Let's see. Like that. Okay. I've analyzed each solution individually. I have the concentration, the volume, how the ions split up. Concentration, volume, how the ions split up. Now what? Well, the next thing is to put them together, mixy, and think, what are the possibilities that could form from these getting mixed together? So on the one hand, I've got, over from this side, I've got the barium hydroxide. And that's going to be combining with the iron sulfate. Should have centered that better. What are the possibilities that could happen if these mix together? Like if instead we got, let's put the barium with the sulfate, and let's put the iron and the hydroxide together. So we're gonna do a wipe swap. So now we've got Ba combining with some of these SO4s. I'm just looking, the Ba with some of the SO4, the sulfates. Those could combine. And the iron here could be combining with the hydroxide there. So those are my 2 choices, right? When I mix this and this, they switch partners, and I'm either going to form barium sulfate, just one of each, or iron hydroxide. I need 3 of this guy so that they match. These are our 2 possibilities. These are the 2 products. These are the 2 products that would form. And the question is, are either of these going to precipitate, aka turn into a solid? So far, so good. Hopefully, rewatch that part if you're having struggles. Now, how do we know if these are going to be a solid or not? Is there like a threshold value or something that we can like compare? Is there like a threshold And if we exceed it, then it precipitates, and if not, then it doesn't. Because that would be really, really convenient if there was some sort of a threshold value that we could look up and see, is there a potential value? See where I'm going with this? So what I did is, I think I got these from this table in the notes. I did. So we have barium sulfate and then the iron hydroxide. I just looked these up in my table. Barium sulfate, 1.1 times 10 to the negative 10. And then I must have got the other one from somewhere else because this table doesn't have it. But looky down here. Looky. Barium sulfate, iron hydroxide. Those are the ones that we're looking at in question. Does the barium sulfate, do we cross its threshold? Iron sulfate, do we cross its threshold? Because down here, that's what the KSP is telling us. We are trying to see if we cross this value for our beaker mixed together. So let's try and figure this out. Let me zoom out a little bit. And probably a little bit more. Actually, I don't know what I'm doing. I do, but I don't know how I want to frame it. Okay, so for barium sulfate, I'm going to use a different color. Barium sulfate, solid, equilibrium, barium sulfate. That's the K value. What would be the K expression? Well, the K expression down here, I'll write it down below, would be products over reactants, get rid of the solid. So I have the barium is one of my products, the sulfate is the other. Neither of them have numbers in the front, so we don't have to raise it to any special powers. This would go on the bottom, but it's a solid, so I'm not going to write it. And this is equal to K. K for this reaction is equal to 1.1 times 10 to the negative 10. So to decide to see if this will precipitate, we need to see do we exceed this threshold? Because if so, then it's going to precipitate. So I'm going to take the Q right out of the middle because this equals this equals this. Let me just eliminate Q from the equation, or sorry, let me just eliminate K from the equation here. Just kind of turn that into one big fat equal sign. And let's figure this out because we got to see in our new beaker, do we exceed this threshold? So up here, back up at the top, these beakers get mixed together. We had 80 milliliters and 20 milliliters. 80 and 20, when you mix those together, how much is going to be in the new beaker? 80 milliliters, 20 milliliters. I'm thinking that combined, when we mix those together, whoop, whoop, mixy, mixy, we should have 100 milliliters because 80 plus 20. But I don't want milliliters, so I'm going to change that to be 0.1 liter. The 0.1 liter, we'll worry about that later. But what we're trying to look at is, does the barium sulfate exceed this threshold? Where is the barium coming from in this thing? The barium is coming from this beaker up here. What do we know about this beaker up here? We knew that there was this many liters of the barium hydroxide. We also knew the concentration was, let's see, concentration is moles per liter. So I'm going to pull this number, 1.0 times 10 to the negative fifth moles per liter. This is just the concentration. And for every 1 mole of barium hydroxide that I had, I was getting 1 mole of the barium ion, right? So how much barium is in this beaker? Because the amount of barium that was in this beaker got poured into here. So let's math that. I'm getting 8.0 times 10 to the negative 7th moles. This is how many moles of the barium are going into this beaker from the OG beaker. That's cool. All right, now we're going to do the same thing, except for what's the other component? We're looking at barium sulfate. Where's the sulfate coming from in this beaker? Sulfate came from this beaker over here. What do we know about this beaker over here? We know that the volume was that. The concentration is this many moles per liter. And for every 1 mole of Fe2SO43, we're dealing with the sulfate. Remember, we're trying to figure out sulfates. For every 1 of those, we're getting 3 of the sulfates, right? Because it's sulfate 3. So T the game, we're taking a break. So far what we've done is we started out with our beakers. From beaker 1, I was like, tell me about the barium. I did some maths and I figured out there's this many moles of barium that are now in this beaker. from this beaker, I said, tell me about this beaker, blah, blah, blah. Maths, there's this many moles of, I should label this, SO4 2 minus of the sulfate. All of this is in here. I'm going to write it. In this beaker, I have mixed 8.0 times 10 to the negative 7th moles of barium. I also have mixed in 6.0 times 10 to the negative 7th moles of SO4 2 minus. I am so close. I'm so close to being able to finish this problem because I now know how much barium and how much sulfur is in the beaker. But why can't I just take the 8, plug it in here, the 6 number, plug that in here? Why can't I just put those in here and see if it's more or less than the threshold? Why is that not the last step? And it almost is. It almost is. It's just that the brackets like this mean molarity, like concentration. So we have to figure out moles per liter and then put that in the bracket. So we're so close. This is moles. This is moles. These are moles per liter. We know how many liters it is. So let's just do moles divided by liter, plug it in. Moles divided by liter, plug it in, and then see if it exceeds the threshold. So since I already have this one pulled up on my calculator, 6 times 10 to the negative 7th moles divided by liter is 6 times 10 to the negative 6. That's the concentration. The other one, 8.0 times 10 to the negative 7th. That's how many moles in my 1/10 of a liter. I'm plugging in the molarities. And let's see, because if this number, when multiplied together, is greater than the threshold, then we get a cool precipitate. But if not, then we don't. So 8 times 10 to the negative 6 multiplied by 6 times 10 to the negative 6. All right, moment of truth. Equals, what does red and blue mean? Purple? Do I have a purple marker? I do. Multiplying those together equals 4.8 times 10 to the negative 11. This is the value that we're calculating. Is this greater than, less than, or equal to 1.1 times 10 to the negative 10? We're comparing it to that threshold. 10 to the negative 11 is smaller . 4.8 times 10 to the negative 11th is smaller than 1.1 times 10 to the 10th. So if you did this exact experiment and you took 80 milliliters of this barium hydroxide and 20 milliliters of this iron sulfate and you mixed them together and you were like, watch this, and you try to show your friends the really cool precipitation that just drops from the beaker and looks so magical, is it going to happen? And our math here is telling us that it wouldn't. We did not exceed the threshold. If not, then no precipitate will form. That's what's happening here. But if so, in like a different situation, then yes, we would get a cool looking reaction. So again, big overview. Big overview. Barium hydroxide, iron sulfate. We're like swappy the partners. Our potential solids that could form are barium sulfate. That was one of the potentials. Did that one actually make it to be a solid? No, it didn't, because what we got for the barium sulfate was smaller than the threshold. Oh, good Lord, Miss Oliver. I just realized that all of that was just to decide that this one didn't precipitate. Are you telling me that I got to do all of that again to see if this other one precipitates? Do I got to figure out how much iron there is, how much hydroxide there is, put them together and see if it exceeds this threshold? Yes. Yes, you do. You do, child. But I'm going to teach you a secret trick so that you don't actually have to, because I don't even have space on my paper to do that, even if I wanted to. So let me teach you a little secret. Back to the paper. Oop. After you've done these problems enough, you start to recognize little patterns. Thresholds that are around like -10, -11, -12, something like that, anywhere from 10 to the negative, I'd say if your threshold, as a general rule, if it's between 10 to the -5 and 10 to the -15, you should do the math to double check and see. Because notice we were really close to the threshold. So you should for sure actually do the math. But anything like this crazy pants to the -39, yeah, freaking right. That threshold is so tiny that like the tiniest little speck would push it over the edge. I don't need to do the math to tell you that 10 to the -39th power is so small that any specks that get in that beaker of that substance will be a solid, because the threshold is so small. So that's kind of the trick here that I would do. Let me get a pink marker for dramatic effect over in this corner. Pro tip. If you have a medium level threshold, medium level threshold means do the math. Write it out, Do the math like we did on this problem. And medium level, I'm saying, is like number times 10 to the negative fifth and like 10 to the negative 15th. I would say if you have a number between there, like we did here, we had to the negative 10th, do the math. But if you have a very low, teeny weeny level threshold, like 10 to the negative 39, really? Do you know what that number is? Can I write it for you? 2.6 times 10 to the negative 39. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Just said, I ran out of room at 27. Filling all of this in with zeros for scientific notation. You're telling me that tiny number, the decimal way over here, 0.000026, that's the tiniest number I've ever seen. So for low level threshold, don't do the math. Just assume that the threshold is going to be crossed since it's so tiny, and move on with your life. So the original question, let me zoom out. The original question was, will there be a precipitate if these two mix together? I mathematically proved that this threshold is not exceeded. Barium sulfate will not precipitate. I proved it mathematically, this whole paper. Iron hydroxide, I didn't mathematically prove it, but I know that that will precipitate because its threshold is so tiny that of course we're going to cross it. Okay, there's one example.